Hello students, let's talk about this thing that we call free body diagrams and why we do them. So I will abbreviate free body diagrams FBD, and there's a few reasons why we do this. If we have a problem that has forces on it, we want a standardized way of drawing and keeping track of all the forces that are acting on the object or objects. So when we draw the free body diagram, typically what we do is we want to show the forces that are acting on only one object, right? This will isolate that object and it will sort of declutter the picture so that anything else that's there is taken away and it's not as distracting. They're very easy to draw. You don't need any artistic skills at all because we treat every object as if it's what's called a point mass. And so what we do is we draw each object as a dot. And what I'm going to do is I'm going to draw the dot in the origin of our coordinate system. So right in the middle of the X and the Y axis. From that dot, we draw the forces outward in the direction that they're acting on the object. So sometimes it's a little bit weird because you might have something pushing on the object, like from the left or to the right, but you might have to draw that from the dot outward. So just be mindful of that. I will always keep the x-axis as the surface. So if it's a horizontal surface, no big deal, we have a standard coordinate system. However, if we do have a ramp, like a ski slope or a hill, then we may have to tip our x-axis to stay consistent with doing this. We may also have forces that are on each axis, but it's possible that we may not. We may have a force that's at an angle to one of the axes. And if that's the case, then we will have to use our trig to resolve our forces into the x and the y components so that ultimately we have all of the forces on each axis. This is also true with gravity, right? The weight pulling downward if we're on some sort of a hill. And later on, what we're going to be doing is once we have our free body diagrams, we can see all the forces that are acting on the x and the y axis. And we'll be able to sum up all the forces that are in the positive x direction, negative x direction, positive y direction, and negative y direction. And that will help us to solve our force problems later on. So we're going to abbreviate our forces, typically with capital F for most of the forces. We'll use lowercase f for friction. And then what we're going to do is use subscripts to identify the types of force. Most of the time they're common sense. So we're just going to put a list together of some of the common forces that we'll use in our class. So F with a subscript A, little a, is an applied force. This is sort of generic for anything that's pushing or pulling on something else. Fg is the force of gravity, which is also known as your weight. The normal force is the force that is supported by a surface. So sometimes it's called the support force, but I'm going to use Fn. And the reason why we call it the normal force, and we'll get to more detail later on, is because normal in your math class means perpendicular. So the normal force is always perpendicular to the surface. And then I'm going to use FAR for air resistance. You can use FAD for air drag, but that's a fad, and fads come and go. Other common forces that I'll use, FT for tension. Sometimes textbooks will just use capital T. I like to use F so that we know that we're always dealing with a force. And then lowercase f is what I use for friction. If it's just the lowercase f by itself, that's sort of generically for friction. It could also include air resistance and some sort of surface friction as well. And then we're going to use our subscripts S and K respectively for static and kinetic friction, and we will talk more about those types of forces later on. So what we'll do now is we'll draw a couple of free body diagrams as practice. We've got 4 of these that we're going to draw together. So we've got a car that's driving on the highway with cruise control, so it's not speeding up or slowing down. And then we'll draw what it looks like if the car is accelerating along the highway. What happens if a car is being towed by a tow truck and it's being pulled at a constant velocity, right? Again, we're just going to diagram the forces that are acting on the car in this case. And then lastly, what does it look like if a car is sliding down an icy driveway at a constant velocity? So we'll just do a couple of examples. They won't take that long to do. We'll of course do a lot more work with these types of situations and these types of problems later on, but this is just to get started so that we have some practice drawing our free body diagrams. It's important that we can draw the free body diagrams because that is setting up the foundation for any of the other force problems that we have to do. All right, so let's get going and we'll practice drawing these free body diagrams. All right, let's get started with our free body diagrams. I'm not going to use a ruler for this. You don't really have to. Just make sure that it's as nice and neat as you can make it. So we've got our number one, the car with the cruise control. So I'm just going to draw in my X and my Y axis. And I'm going to make the X axis the surface. So in this case, it's the road. And the car will go right in the middle like this. This one said that we're moving at a constant velocity, like this. So what I'm going to do, actually, you know what, we'll do the forces in a different color so we can see them. So for this particular problem here, we'll have our applied force. We have gravity pulling us downward. We also are going to have the normal force, which is the support force. That's the road pushing back up. And in this case, we have our frictional forces going to the left. And that's it for now. That's all we'll do for our free body diagram. We have our 4 forces that are acting on the object. And we'll do more with these types of problems later, but for now, that's good enough. Let's take a look at our second problem. The second one is now we have a car that's going down the highway or some street, and it is accelerating. So we've got our X and our Y axis again. X axis is the road, but for this problem we have some acceleration going like this. The car will make right at the origin. So in this case, I'm going to make this exaggerated a little bit. We've got our applied force going in this direction, but because I know there's acceleration, I'm going to make sure that the frictional force is less. Right? And so we can see in this case, this force here, this vector is smaller than this one. We don't know how to turn gravity off, so we still have our force of gravity. And we've got our normal force supporting. And that's what we have for our second free body diagram for the car that's accelerating down the road. The third example was the car being towed by the tow truck. I'm going to draw in, again, my X and my Y axis. X axis is once again the road. But now we've got something a little bit different. For this one, we can see that I have a tow truck. And the tow truck is going to be lifting up like this at some angle. That's how tow trucks work. They have to lift part of the car off the ground, the front or rear 2 tires, and then it pulls it forward. So what we need to do then, because we have our applied force here that is not on an axis, we have to resolve our applied force into the X and the Y component so we can see how it fits onto each axis. So I'm just going to drop down a perpendicular line to each axis, and where that meets the axis, now I have FA's X component, and then over here I have FA's Y component. So this diagram is not going to be to scale, but that's okay. We just have to keep track of the direction of the forces. Gravity's still pulling downward. We're still on a surface, right? The road is still there, so we have a normal force also pushing upward, and we have our frictional forces pushing this way. And I believe that this also said, and I didn't write it before, but I'll write it now, that we were moving at a constant velocity to the right. So this one is a little bit more complicated, but once we have resolved a force that's not on an axis onto the X and the Y axis, those are the only forces that I need to worry about, right? I don't have to worry about this part anymore. I'm just looking at what's on the X axis and what's on the Y axis. Okay, so these diagrams here, free body diagrams, were for when we had an X and a Y axis that was pretty much standard. But in number 4, it says that the car is sliding down an icy driveway. We're still going to make the surface the x-axis, but now our surface is tipped. So when I tip this, I'm just going to tip it a little bit. I'm not going to over tip it, but you can see, ooh, that was not drawn very well. Let's get rid of this one. That's pretty good. I'm going to draw in my x and y axis tipped like this. This is still the road, but I believe we called it an icy driveway. So the icy driveway is still the surface, but now our surface is tipped because it's on a hill. The car will still be in the middle, right over here. In this case, it still said it was moving at a constant velocity, sliding down the driveway. Watch out if you're at the bottom. But now what we have is gravity is partly pulling us down and keeping us on the surface. Gravity always goes downward, like this. So what I want to do then is I want to draw in here and label the angle of the driveway. This angle here is the same. If I were to tip this axis so that it was closer to 45 degrees, it would be harder to show that this angle here is the same as this one here. But if I tip it just a little bit, regardless of whatever angle is given, then we don't really have to use much geometry. You can see that this small angle is closer to this side than this bigger side. And that's why I only tip it a little bit. We can also see that our force of gravity is not on an axis. So just like we did in number 3, when our applied force was not on an axis, we have to resolve our force of gravity vector onto its x component and its y component. So we'll put in perpendicular lines to each axis, and then where it meets the axis is where we have our component. So this would be gravity's x component. This would be gravity's y component. We still have a normal force supporting. Notice that the normal force is still perpendicular to our surface. It just happens to be pointing at an angle because we're not on a flat level surface anymore. And we're sliding down at a constant velocity. So I know that there is a frictional force that opposes but also matches that. So here's 4 examples of how we draw free body diagrams. This is how we get started for our force problems. And we'll certainly do more when we talk about Newton's laws and when we talk about the different types of forces, like how we can calculate friction. So give the rest of those a try from your assignment, and I will see you in class.